Trigoners. Welcome to your 4.1 online homework video. We're going to roll through some stuff here. Some stuff will be familiar, some stuff will be new. So let's just start with a quick recap on how to use this calculator to graph in case you've forgotten. If you recall how to do this, you can fast forward this part, but I'm just going to do a quick walkthrough one more time on how to find mins and maxes in your calculator. So right now I'm going to go ahead, I'm going to enter this equation into my Y1. Usually we start with a Zoom 6 standard window. When you do this, I can see that the top, the maximum of my graph is missing. This up direction is again called my Y max. So I'm going to go ahead to my window. I'm going to up that Y max to maybe 25. See now if I can see that maximum. Now it's going to be on my screen so that I can calculate it. So the way I calculate a maximum again is second, calculate, go down, choose maximum. First thing it asks me is to go left bound of my maximum. So I don't have to go super close, but I can see right now I'm left. I'm going to go ahead, I'm going to go to the right, hit enter twice, and you'll see my maximum. Let's round to the nearest tenth. Looks like it was about 1.2 comma 13.1. So that's my maximum or my vertex. And also something we practice calculating were our zeros. Zeros is just another way in the real number system to say x-intercept. So I have a 0 here and here. I'll just practice calculating 1. How about this 0? So I'm going to go ahead, I'm going to go back to calculate. So second trace, or calculate. I'm obviously going to choose the option 0 to find a 0, also known as an x-intercept. It asks me to go left bound of my 0. Looks like I'm above, but I'm just ever so slightly to the left. I hit enter once. I'm going to go right bound now. Looks like I'm below, but again, notice I'm ever so slightly to the right. Hit enter again. Enter a third time. I get about 3.3 comma. Now you're going to notice I know my y value at an x-intercept should be 0. This negative 1 times e to the negative 12th, that means negative 1 times 10 to the negative 12th, which is 0.00000001201. Your calculator's approximating here, so it's trying to get to 0. It got darn close, but it's just a little off, so I'm going to write this in as 0. This is one of my zeros, all right, and I'm going to let you go ahead and calculate that other 0 on your own. You can check with your partner tomorrow, see if you get the same thing. Next thing I want you guys to do is go ahead, pause the computer really quick, and I want you to see if you can get this parabola onto a window on your screen. So go ahead, hit pause. All right, now you can go ahead, you can check with me, see if you get the same thing. 12x squared plus 17x minus 32. My hope is that you actually did try this on your own, but as I look at this right now, I know that my y-intercept is at negative 32, so I may want to adjust my window to go down to like negative 40. I'm going to go ahead, I'm going to hit graph. I'll leave my y max the same as my last problem. I'm going to see if I see this parabola. All right, because I used this clue, my y-intercept, I knew that I could adjust my window so that I would see the y-intercept at negative 32, and I actually was able to see the whole minimum as well. If you need practice right now, go ahead, calculate those zeros in the minimum here. You're going to notice I have a little bit of excess on my x max and my x min. If you wanted to chop some of that off, let's say to negative 5 or 5, your parabola then would take up a little more of your screen if you prefer. Not necessary, but just so you know. All right, if you calculate the zeros in the minimum, you can check in with those with your partner tomorrow. All right, now a couple words that we've used a little dangerously but interchangeably have been these words: x-intercepts, zeros, and roots. Now, this only holds true if we're working in the real number system. You're going to find out today that x-intercepts and zeros may actually mean different things when I'm also considering complex numbers. Remember those i's, numbers. All right, when I comes back into the picture, x-intercepts and zeros will actually not always be the same thing, and we'll take a look at why that's the case. All right, so something that we're going to look out for. We've talked about degree. We talked about that in class on Monday. The degree is going to tell you how many numbers of the number of zeros or solutions that each problem has. Now remember, we used to use the word 0 interchangeably with x-intercepts. That's actually not going to be the case anymore. So I'll explain what I mean in just a second. Here I can see my degree is 1, which means I'm going to have 1, 0. All right? It could be real or complex. Now, obviously, this is a line, 3x minus 1, with a positive slope. We can see that my 0 here is actually an x-intercept. Stay with me. This is kind of new. Here, I have a parabola. This is telling me the highest degree is 2, so I'm going to have 2 zeros. Right here, highest degree is 4, so I'm going to have 4 zeros. Now these zeros might be real or complex. They're not necessarily x-intercepts. Here, I see the highest degree is 7, so this is the 7th degree polynomial, trinomial in this case. So this means it's going to have 7 zeros. They may be real or complex, depending on the question. Before, you guys used to say, well, if my parabola, for example, hits twice, I have 2 zeros. Sometimes your parabola would hit once, and you'd say, I have 1 0 or 1 x-intercept. And sometimes your parabola would hit 0 times, and you would say there was 0 solutions, or 0 x-intercepts, or 0 roots. But what we're going to find out today is that this parabola, it has a degree of 2, meaning it has 2 solutions, or 2 zeros, and those zeros will actually be complex. Let me give you an example now. So here's something that's really familiar. You know this is a parabola that's been shifted down 1, 2, 3, 4. So if I drew this parabola, you'd see pretty quickly that there are 2 x-intercepts, 2 zeros. Degree is 2. But if you were to solve this algebraically, to find the zeros, you'd set it equal to 0. You'd add your 4 over, x squared equals 4. Square root both sides, so square root. You'd get x equal plus or minus 2. You'd see your 2 x-intercepts are your zeros. However, look at this next problem. You guys know your transformations quite well at this point, so you'd say that's a parabola that's been shifted up 4. We know that that parabola never hits the x-axis, so it has no x-intercepts. Our inclination would be to say it has no zeros, all right? But it actually has no real zeros. If I were to solve this thing for the zeros, I'd set it equal to 0. That's a plus. I'd subtract my 4 over, square root both sides, and if I'm working with complex numbers, I now know that x can equal plus or minus 2i. So I look at my degree, I knew it had 2 solutions, or 2 zeros. It just so happens that the zeros are complex. We can't see them as x-intercepts on this graph, so there are no x-intercepts, but there are 2 zeros, right? And they happen to be complex. So this degree tells us how many solutions there are, how many zeros, but not necessarily if they're real or complex. That's what we have to solve for. All right, so let's go ahead. Let's look at something a little more complicated. So go ahead, turn the page. We're actually going to look at the graph of some more complicated polynomials. If you threw this in your calculator, this is the graph that would show up. In fact, let's go ahead. Let's do that together. So take out your graphing calculator. In your y equals, let's clear out that old equation and let's put in 3x cubed minus 4x squared minus 20x plus 9. All right, I'm going to go back to my standard window, which hopefully we're all familiar with by hitting zoom 6, and I'll see this on my graphing calculator. Now because I actually gave you this picture already, you can see that it looks like I have a little too much of my x's and I need to see a little higher on my y max and my y min. So let's go ahead, let's cut off my y or my x max and x min just a little bit, and let's go down a little further, maybe to negative 20 and 20. Let's see if that's enough. Go ahead and hit graph and let's see if we get a better picture of this. Looks like I'm still missing my relative max and my relative min, so I'm going to go ahead, I'm going to adjust my window one more time. Let's go to negative 30 and 30. That should cut it even way more than I need, but there we go. Now I'm seeing a better picture of this. So when I ask you for increasing or decreasing intervals, that's something that we've done before. Remember, we always read a graph like we read a book. So we'd read it from left to right. So it looks like here from negative infinity all the way up to this point. We don't know what that is yet, but we'll find it. I'm increasing. From this, we call this point a relative maximum, and this point a relative minimum. I'm decreasing. The reason it's called relative maximum, because it's actually not the highest point on the graph. If you look over here, I'm going to continue to get higher. So just relative to what's around it, we call it a relative maximum. We call this a relative minimum, again, because it's just relative to what is around it. It's lower, but actually the graph gets much lower over here. So here's my increasing interval, negative infinity up to this point, which we can calculate, decreasing from this point down, and increasing again from this relative minimum up. All right, now turning points occur where the graph goes from increasing to decreasing. So we'd say that this is a turning point, and here we go from decreasing to increasing. This would be a turning point. So I think this would be a good time for us to go ahead and calculate this relative maximum. So we're going to calculate this just like we would an old maximum. So go ahead, hit second, calculate, go down to maximum. All right, it asks me just like before to go left bound, so I'm going to go ahead and go left, hit enter once, go right of the maximum, hit enter again, enter a third time. All right, and I get that point to be about negative 1.1. So let's mark this. Negative 1.1, comma, 22.2. 22.2, and I'm going to go ahead, I'm going to calculate second, calculate, go down to minimum, hit enter. All right, I'm going to go scrolling over kind of slow. All right, I'm going to go left bound, hit enter once, go right bound, hit enter again, enter a third time, and I find that relative min to be about 2, comma, negative 23. So my increasing interval occurs from negative infinity, comma, 1.1, bracket. And I also have another increasing interval from here to here. So I'd say the other increasing interval occurs from 2 to infinity. So those are my increasing. My decreasing interval occurs from here to here. That's where my graph is going, down. So that occurs from decreasing from negative 1.1 all the way up to 2. All right, my turning points are what I just listed. It's where the graph actually changes from increasing to decreasing, or vice versa. My other turning point would be 2, comma, negative 23. Now what's new here is actually something called end behavior. We've actually sort of done this before, but I'm going to teach you a new notation. We used to say as x goes to infinity, y goes to infinity. All right, and we would also say as x travels to negative infinity, so as x goes this way, what direction do my y's travel? Well, they travel down here to negative infinity. Y would go to negative infinity. But since we're honors kids and we want to get this notation, we're going to use a new notation. Looks like this. I'm going to say the limit of this graph, so I'm talking about the graph y equals, as x travels to infinity, y travels also to infinity. This is calculus notation. I do want you guys to be familiar with it. Again here, the limit as x travels to negative infinity of this graph of y, the y is going to travel to negative infinity. This notation is going to take a little bit of practice. All right, total zeros. Well, when I look up here, I see that I have 3 total zeros. The real zeros are going to be where the graph crosses the x-axis. So here I can actually see that I have 1 x-intercept, 2 x-intercepts, 3 x-intercepts. So I have 3 real zeros, which means I must have no complex. All right, I'm going to have to, I can only record 15 minutes at a time, hit stop here. And let's go to a second video just to get through one more example, and you should be set. If you're having questions, hopefully you can discuss some of these things with your partner tomorrow. And if not, we'll just go through more stuff together on Thursday. Okay?